Okay, and now Alex will bring us down to earth and talk about large-scale motion in the core.
So good morning, everybody. I would like to thank the organizers of the workshop for inviting me, and also the attendees and the staff at INI for a very enjoyable workshop. So today I'm going to talk about large-scale core flow. So this is the slow flow, according to Julien's description on Tuesday, the flow that varies on secular decadal timescales. And that will also give me the opportunity to present results that we obtained from a novel numerical simulation that we performed together with Thomas Gastine. So this is a plan of action of my talk. I will begin by describing observations and inference of large-scale core flow and the type of constraints that they place on dynamo models. And in the second part, I will discuss how a few Boussinesque simulations that I picked can meet these constraints. So it all begins at the core mental boundary. So this is a map you've seen before. It's a radial component of the magnetic field at the core mental boundary in 2022, according to the 7.12 version of the chaos model by Finlay and colleagues. So the field is dipole dominated, and it also features a number of smaller scale patterns, such as these fluxes of reverse polarity underneath the Atlantic Ocean. So if we draw the same map in 2002, that is 20 years before, we notice that the patches have moved eastward. So that's an indication of the westward drift of these patches with time, and so that's an indication of the westward drift of the geomagnetic field. So we can take the difference between these two maps and divide by 20 years. We obtain the average secular variation over the time interval I considered. And we see that these maps is presenting a hemispherical dichotomy, in the sense that the secular variation is much more intense in what is so-called the Atlantic hemisphere. There is almost no activity in the Pacific hemisphere, and this activity under the Atlantic hemisphere takes the form of intense patches at low latitude, but also at high latitude. So if we want to make sense of this map, we go to the induction equation that relates the rate of change of the field to the competition between induction by the flow and diffusion. The ratio of the two terms on the right-hand side is also the ratio of the magnetic diffusion timescale to the convective or advective timescale. This is the celebrated magnetic Reynolds number. And since our knowledge of the secular variation is restricted to the surface of the core, we take the radial component of the induction equation and write it down at the core surface, and this is the equation that describes the dynamics of BR. So again, transport by fluid flow and diffusion. Diffusion comprises two components, a horizontal one and a radial one. Now, if we take an estimate for the value or magnitude of U, the estimate of the velocity drift of these patches we look at, we find that this transport term for large scales is much larger than the diffusion term. And so we end up writing the frozen flux approximation. So this is the contribution by Roberts and Scott, 1965, that Chris mentioned yesterday. So we are in the frozen flux approximations. We know dTBr. We know BR. So we can try to solve for U, subject to some additional constraints on the flow. So this is the realm of the so-called core flow problem. So be careful there, because as easy as it may sound, the core flow problem has become some sort of a craftsmanship. And in particular, Nicolas pointed out on Tuesday that it's extremely important, in particular when you're looking at satellite data, to include the effect of the unresolved small scales of the field and the flow on the resolved large scales of the secular variation. So in any event, we can look at the pattern of the flow in 2012. So this is the central epoch of the time window I considered. This is a flow model from Gillet and co-workers that rests on the COVOPS X2 field model. So you're looking at the motion of particles at the top of the core. So you see that the flow is particularly important, well, underneath the Atlantic hemisphere, that it possesses a rather large level of equatorial symmetry. The color refers to the flow speed, so it can go as high as 45 kilometers per hour. And in particular, you see that at high latitude there is a rather strong patch of velocity. So if you want to look at this patch in more detail, you can draw the same map, but looking down from the North Pole. And so you see that the large-scale flow in 2012 at the top of the core takes the form of this large-scale eccentric gyre that we heard about many times this week. So the flow is particularly intense underneath the Atlantic. It goes up, goes around the tangent cylinder, and is particularly strong here with underneath the Bering Strait with velocities as high as 45 kilometers per hour. So we have an idea of the large-scale flow. We can take 10 kilometers per year at the root mean square flow speed with a large length scale of 2,000 kilometers with a standard value for the magnetic diffusivity of 1 meter square per second, and we find why it is so nice to look at the geodynamo rather than the solar dynamo. We find the magnetic Reynolds number equal to 1,000. If we further assume, if we do not listen to Dominique, and we further assume that the flow is perfectly axially invariant, and we can take, on the account of the fact that the Earth core is a rapid rotator, we can compute an estimate of the total kinetic energy that is carried by this flow, and it's on the order of 8 times 10 to the 16 joule. So that's a snapshot, and so we may be interested in knowing how this flow evolves in time. So what I did next was to look at the average of the flow using Nicolas' model from 1950 to 2020, so 70 years, so approximately half a turnover time. So you see that the flow kept its overall geometry. Maybe it lost a little bit of its intensity here, but it remains that this is a remarkably stable feature. And so what I'm going to do next is to try to get a feeling for the time dependency of the flow by placing virtual velocity sensors at the core mantle boundary underneath the Atlantic. So you're looking at the fluctuation of the azimuthal velocities there between 1880 and 2020, which is the time span of the flow model that Nicolas computed. So what you see that overall you've got an average value of 15 kilometers per year westward, that there are signs of decadal fluctuations. And you can also notice that more recently, there's higher frequencies that are contained in the signal. And these may be an indication of the waves that we heard about earlier this week. And it's interesting to notice that we start to get this higher frequency content at about 2000, which is precisely when we started to monitor the changes of the field using dedicated satellites. And so let us hope that this careful monitoring will continue after the swarm mission ends. If we now place a ring of sensors at high latitude, we see that there is overall a westward flow with a mean value of about 10 kilometers per year, and we see that indeed underneath the Bering Strait here, with the blue and the orange sensor, there's been an acceleration of the flow there from, say, 20 kilometers per year westward in 1980 up to 40 kilometers per year in 2020. And so this observation of this acceleration of this jet came to the fore in the wake of a study by Livermore and colleagues in 2017. So what they did was they computed a local core flow inversion able to account for the motion of the patches of secular variation at high latitude. So this is the profile of the jet that they came up with. So the top velocity is about 45 kilometers per hour. The jet extends across the tangents.
Per hour, per year.
Sorry, Sasha. Yes, okay. I kept on saying per hour since the beginning? All right, so okay. Can we? No, we won't. We'll post-process that. So yeah, everything I said was per year. All right, apologies. Okay, so in any event, the jet extends across the tangent cylinder, top velocity 45 kilometers per year. And the origin of the jet has to be in a dynamical contrast across the tangent cylinder. So there can be either an inhomogeneous distribution of magnetic field, in which case the driver will be the Lorentz force, or an homogeneous distribution of the density anomaly, in which case the driver would be the buoyancy force. Okay. So the last bit of observation I want to talk about, well, you saw that also this week, about the detection of torsional waves propagating in the core. So this is a time cylindrical radius plot of the geostrophic velocity, the velocity of geostrophic cylinders. So what we see is that these waves propagate from the tangent cylinder to the core mantle boundary in about 4 years, not 4 hours. And then the amplitude of this signal is relatively weak. It's about 0.4 kilometers per year. Okay. And so, but in any event, the fact that the travel time is inversely proportional to the cylindrical radial component of the magnetic field allows us, under the assumption of isotropy, to come up with a root mean square estimate for the strength of the field inside the core, this 4 millitesla, that give you magnetic energy on the order of 10 to the 21 joules. That is much larger than the kinetic energy. So the synthesis of this constraint is the following. We have a dipole magnetic field. The secular variation tells us that the magnetic Reynolds number is 1,000. It also allows us to come up with an estimate for the kinetic energy. We look at torsional waves. We find out that the magnetic energy is much larger in the core than the kinetic energy. And the large-scale flow is stable on decadal to secular time scale, eccentric gyre that contains a time-dependent jet. Okay? So now the question that we're going to ask is how can dynamo models account for these various observations and constraints. So I will start with the Coppolder's model by Aubert and colleagues. So the Coppolder's model is remarkable in the sense that it can account, in a statistical sense, to all the properties that I listed. It has a magnetic Prandtl number of 2.5, an Ekman number of 3 times 10 to the minus 5. The magnetic Reynolds number is 900, and the ratio of the magnetic to kinetic energy ratio is about 2. So it accounts for the morphological properties and also the statistical properties, the hemispherical dichotomy of the secular variation of the Earth's magnetic field. It's a thermochemical dynamo model, but in order for this model to reproduce and explain the gyre, one has to add 2 ingredients to the standard dynamo cocktail. Okay, and these 2 ingredients are the following. The first one is the gravitational coupling between the solid mantle and the inner core. So what happens is that as plumes chemical plumes are emitted at the inner core boundary, they are subject to the Coriolis force. So they tend to entrain the inner core in the eastward direction. If there is coupling between the inner core and the mantle, then the mantle is also entrained in the eastward direction. So then what happens is that conservation of angular momentum demands that the outermost part of the core to flow westward. So that would give you an m equals 0 gyre flowing westward at the top of the core. Now, if you want to get your m equal 1, so if you want to get your eccentricity, then you need an extra ingredient, and the extra ingredient rests on the assumption that the crystallization of the inner core is not homogeneous and that it is, in fact, fastest underneath Indonesia. So that creates a hemispherical buoyancy release. The buoyancy release is stronger underneath Indonesia, which causes the eccentricity. Okay? So this is a model that ascribes a convective origin to the gyre and its eccentricity at the expense, if you will, of Occam's razor, in the sense that you cannot achieve this agreement without these extra ingredients. Okay? So the second simulation which I'd like to talk about is the step 2 simulation by Schaeffer and colleagues. So this is an extreme direct numerical simulation that we heard about before this week as well. So it's the boundary conditions there are no slip at both ends. There's homogeneous fluxes of the condensities that are imposed on both sides. So the inner core is insulating and it's non-rotating. The Ekman number has a value of 10 to the minus 7. The simulation is about 100 times supercritical, and it's a very dynamic simulation. It was integrated for about 5% of the magnetic diffusion time. So that echoes what Bruce was saying earlier this week about the difficulty or the impossibility to integrate these extreme simulations over long time scales. The ratio of the magnetic to kinetic energy is about 13 on average. It's a turbulent simulation with a Reynolds number of about 5,000. And it's been run with the XCL's code, which is an excellent code to tackle a variety of problems in spherical geometry. So this is the magnetic field in the simulation. The surface magnetic field is dipole dominated, and the interior dynamics of the magnetic field is extremely rich, and the magnetic field is particularly strong inside the tangent cylinder. Okay, what's interesting also with this simulation is that if you take the Z average, so the average of the flow along the direction of rotation, and you time average it, you get this pattern. So that would be the equivalent of the result of a core flow inversion performed on this model. So you find an eccentric circulation that also has an m equal 1 pattern. It does not circle around the tangent cylinder, but nevertheless, you get this, this banana shape without prescribing any heterogeneous boundary condition. So it emerges spontaneously from the simulation. You also get, on time average, very intense westward vortex inside the tangent cylinder. So that's interesting. And so recently, Ori and colleagues, so Kumiko, Steve, and Chris, speculated that this banana could in fact correspond to a soliton, that is a solitary magneto-Coriolis wave. So it's interesting in the sense that it would ascribe not a convection origin, but rather a wave-based origin to this large long-term feature. So that's one of the reasons, that's not the only reason, why Thomas and myself decided to run a simulation similar to step 2, but with a few differences. So I'm going to talk about it now. So the boundary conditions are still no slip and homogeneous, but this time instead, we're driving the system by imposing a temperature contrast across the shell. Okay, so it's a delta T forcing. The Ekman number is still equal to 10 to the minus 7, and the magnetic Prandtl number to 0.03. So we integrated the simulation for about 13% of a magnetic diffusion time. The ratio of the magnetic to kinetic energy is on average equal to 8. And it's a turbulent simulation that we run using the magic code, which is also a very useful tool to consider a variety of problems in spherical geometry. Okay, so this is the temperature field in the simulation with, again, very active dynamics inside the tangent cylinder, and overall the tangent cylinder is much hotter than the surroundings. So there is a very active dynamics around the rim of the tangent cylinder. So this is now a movie of the azimuthal component of the velocity. So outside of the tangent cylinder, you see signs of axial invariance, and then a very strong westward current here along the rim of the tangent cylinder. So what I did was to wonder whether this sort of active zone could be detected if we were to conduct some measurement survey. So I computed the intensity predicted by the model at the surface of the Earth, look over the duration of the simulation, which is about 200 Alfvén times. I looked at the fluctuation of the intensity it predicted, and I drew a map, which is shown here. So this is essentially a measure of the standard deviation of the velocity of the intensity as would be measured at the surface of Earth. So the fluctuations are stronger at the poles than at the equator because the field is stronger at the pole than at the equator. And what's interesting here, looking from the North Pole, is this region of high fluctuations of intensity that sort of maps the current that we see here on the left. So the field is dipole dominated. So we check that box. So it's dipole dominated with features of smaller scale, also large scale features such as this patch here. And if you monitor the compliance of this field with the historical field, so this is the Chisquare measurement that we heard about, for instance, it was on Wednesday with Chris Davis. You see that most of the time, in fact, the field that is produced is not compliant with the historical field, and that's mostly on the account of it being too dipolar. Nevertheless, there are times during which it can be in good or even excellent agreement with the recent historical field. If you now look at the ratio of magnetic to kinetic energy, so it fluctuates over those 200 Alfvén times between 15 and 5. So what I did on the right here is what I selected the two time intervals 1 and 2, and I plotted the kinetic and magnetic energy spectra for these two intervals. So when the field is strong, dipole dominated, then you see that the spectrum of energy peaks at a scale larger than the one at which it peaks around here when the field is weaker. Okay? And you also see an indication for an inertial range here with a slope of about 1.5 or so. To illustrate how the magnetic field talks to the velocity field in terms of constraining the velocity field topology, I plotted here at times where the magnetic energy is rather strong, the density of magnetic energy in a meridional plane, and 30 times the density of kinetic energy in the same meridional plane at the same instant. And what you see is that at places essentially where the field is strong and there is almost no flow, and conversely in those regions where the field is weak, then you can get substantial flow. So that clearly shows that the field, via, I guess, magnetic pressure, exerts control on the topology and the organization of the flow inside the domain. What I'm plotting now is the force balance for these two epochs, large ratio, small ratio. So what we see, again, we've seen that before, is that at zero order, the balance is between the Coriolis force and the pressure gradient. And then the next order balance is between what's left when you take the difference of Coriolis and the pressure gradient in green, the buoyancy force, and the magnetic force. When the magnetic force is weaker, when the field is weaker, then the flow happens to be 20% more geostrophic than when the magnetic field is stronger. In fact, the magnetic field is strong when the field inside the tangent cylinder is extremely strong. Okay, and in those situations, the ratio of the kinetic energy that is contained inside the tangent cylinder is about 20% of the total kinetic energy. When the field is weaker, this ratio goes down to about 12%. Okay, so even though the tangent cylinder occupies something like 14% of the volume of the core, there can be a more than average amount of energy stored in the tangent cylinder when the field is strong. Okay, so strong field, strong flow in the tangent cylinder. This shows as well when I do the same exercise of computing the average of the flow and average it over some time. The time I chose there was 10 Alvan times. So I did the equivalent of what Nathanael did for the banana plot that I showed before. Okay, so this is the circulation that I get. And the color scale this time is the intensity of the flow. So when the field is rather large, we get also a strong eastward vortex inside the tangent cylinder, which is much weaker at times where the field is lower. But you don't really get any banana there. You'd rather get a chain of olives or something like that. And so there's no spontaneous emergence of an m = 1 mode in this setup. Okay? And, well, that may be connected to the boundary conditions that we imposed on the temperature. Okay, time to conclude. So, yes, so dynamo models can produce dipole-dominated field. Well, thank you for that one, Alex. They can achieve a magnetic Reynolds number of 10 to the 3. The most turbulent simulation don't really achieve a clear, can achieve the magnetic energy on the order of 10 times the kinetic energy, but not more, if they are turbulent, because of the difficulty of their numerical integration. For what regard the new simulation that I showed you, so the large-scale flow in the core in this simulation is controlled by again by a QGMAC balance. The strong westward jet that we find, and that also we found with Nathanael in step 2, is confined inside the tangent cylinder, which is a very strong dynamical barrier. Okay? And so this happens when the field is strong inside the tangent cylinder as well. And we do not get, and that's a bit disappointing, the spontaneous emergence of an eccentric large-scale geostrophic circulation. And that's why we need to look more into the reason for what that would be, but it is perhaps connected to the different boundary conditions that we impose on the temperature. And I will leave you with that. Thank you.
So, thank you, Alex. I'm sure there are many questions. Who wants to start? Far away. No. Okay, first, Uli, is that okay, Christoph?
I wonder if there's an opportunity to test if in your core really the magnetic field inside tangent cylinder is on average stronger than outside by looking at inward migrating torsional oscillations, for example. Did anyone look at that, or question to everyone?
Observers, where are you?
No, I think the back, yeah.
Ah.
We have the Grenoble gang in the back. So your idea would be just to estimate the strength of the field by monitoring inward propagating torsional waves. Okay.
So in simulation of turbulent simulation of the kind of what Alex and myself did, inside the tangent cylinder it's very shaky. you get a lot of action going on, and we couldn't see torsional waves on top of this. You have this strong twisted vortex that oscillates and moves around, and I think this dominates the dynamics, and I think it will be hard to find torsional waves inside. Somebody has to start harder, I think.
So I have looked at that when we perform core flow inversions, but I have to stress that the polar cap is a very small area at the surface of the core, so the confidence I get in these flows is little. And one of the main reasons for this is also the difficulty of having a clear signal of what's going on at high latitudes, because that's where the magnetic signal is the more complicated with all the field line currents and so on. So in the models, you can, flow models inverted from the data, you can see some inward propagation at some epochs, but okay, we need to work more on that maybe, but I think it is a difficult task. But maybe there is some information that we did not completely extract.
Okay, now Christophe.
Thank you, Alex. I was just wondering how equatorially symmetric is this activity in the tangent cylinder? How equatorial, what is the equatorial symmetry of that, if you compare North Hemisphere and South Hemisphere?
Well, they don't, I mean, they are almost independent.
Okay.
Yeah, yeah.
So, you can see in both hemispheres and it's uncorrelated.
Yes.
Okay.
Alex, I'm, well, too lazy to drive this lower Ekman number simulations. Why is that essential to have an Ekman number of 10 to minus 7 rather than 10 to minus 5 or so in coupled Earth? And so the dominance of the magnetic energy or Lorentz force is important to
that
get these
too,
ones?
and I would say that if you reduce the diffusivities, you get a larger value for your Lundquist number. And so you have the chances that you get wavy signals is increased.
So is it a wave?
For this solid, what?
Is it a wave? Is it a wave?
Well,
There's only flow inside the TC. Is it a wave?
well, but you know this banana may very well be a Soliton.
So the M equals
It's a large
1.
scale.
Okay.
So no, it's a large scale feature. So you can take the large scale to estimate the Lundquist number. You do that for step 2. You find something like 1,000. So by decreasing the value of the diffusivity, you crank up the Lundquist number, and you give yourself the opportunity maybe to witness the emergence of these features. If you want to have a wavy interpretation of these features, which the more I think about it, the more tempted I am.
Yeah. So the Soliton idea, Sasha, you're next, okay? So the Soliton idea, is that proven? I missed that paper by Kumiko. Was it Kumiko or who was that? Kumiko?
It was Kumiko, Steve, and Chris. They're all in the room.
They're all in the room. Who wants to?
Yeah.
Okay.
What is the question to Kumiko, Johannes?
You can repeat the question. So the question was this M equals 1 gyre. Is it a Soliton, yes or no? There seemed to be a suggestion that in Nathaniel simulation it may be a Soliton.
Well,
Maybe
the Lundquist number is such that it could be wavy. That's what, because it's large scale, so it's possible. Yeah.
I mean, that's the sort of the free mode oscillations or free mode solutions, so they don't assume any excitations for that particular wave pattern. Once you have any mechanism or excitation to drive that pattern or launch, that pattern at first, then that could last persistently, well, as long as the diffusion comes in.
So it's a possibility, I understand.
Yeah, I think that Nathaniel may had a
You have an answer to that, good.
Yeah.
No, I have no answer. I had another question. Why do you say, Alex, that the difference with Nathaniel simulation is related to the thermal condition and not the magnetic condition on the inner core. If I understood well, you have a conducting inner core.
Yes, but because the inner core is small, first of all, and so but by imposing the temperature, you don't allow really temperature gradients, strong temperature gradients to develop in the vicinity of the outer boundary. And so I remember that this m=1 banana in the simulation was, Nathanael, you can confirm, it is associated with an m=1 temperature anomaly mode. And it's easier to get an m=1 temperature anomaly mode where you are imposing fluxes on the outer boundary rather than the temperature, because imposing the temperature is just killing any lateral temperature gradient. So that's why I think that this is where to look at first, yes.
Okay, Sasha.
Different question. It's certainly naive for you guys. We are starting with all the exoplanets we have around stars that are close to look at the influence of tides on cycles and magnetic activity in stars. So of course we know the dependency. So I was wondering if there are any records that we could have some influence of tides in the dynamics of the iron liquid cores, and if we could have some bias. Has this been studied for the Earth dynamo? Because we are starting to look into that for dynamo and exoplanets, because we have like Tobu, for example, has a very short cycle, and so it may not be the case, but I was wondering if you can easily impose harmonic forcing in your dynamos to take into account some tides. And I was wondering if that has been looked into the geodynamo community.
Yes. So there's alternatives to the convection-driven scenarios that are connected with the variations of the rotation rate and the perturbation of the orbit of the Earth.
Not necessarily speaking of the reverse, or more about having some.
In the data, there was a few papers by Aldridge in the 1990s, and I think that he was looking for oscillations in the record with periodicities that would be related to, I think, the precession of the axis of rotation. But honestly, I'm not super sharp on this. So that there's been, but it's not the most accepted scenario. Although, well, we're not going to open Pandora's box here, but if the conductivity is really large, then if you have no inner core, you're getting some trouble in driving your dynamo 3 billion years ago. And so the alternative there would be to consider tidal forcing, because it was stronger at that time. And so that's, but that's something that has not been looked at in a systematic way, such as convection-driven dynamos. Yeah.
Alex, I wanted to come back to the relationship that Andreas mentioned yesterday, possibly between the gyre and the South Atlantic anomaly. So I wondered, do you see any evidence in the dynamo simulations for connections for where, I mean, you mentioned regions where the field strength is low. So is the gyre in your mind connected with the South Atlantic anomaly, or are these completely different things? Both are m=1.
Well, to test this idea, you need a gyre, consistent one. So I guess this is something that you could test with cup holders or even further down the path. I'm sure that the gentleman sitting over there has looked into this possibility. Julien, did you try to see?
Intensity anomalies, you mean?
Yeah.
I've not looked specifically into that, but I know that when I do data simulation based on the cup holders
prior,
then the result of the system wants to put the flow next so that the main South Atlantic gyre encircles the South Atlantic anomaly in such a way that basically you get the classical high magnetic energy, low flow configuration that you alluded to, and the flow encircling the concentration of magnetic.
Thank you, Alex, for this very nice talk. I was wondering, because you show this nice plot of the chi-squared, the time series of the chi-squared in your DNS.
Yes, yes.
Have you computed the same for S2 Nathaniel dynamo? The underlying question is, do you think this thermal boundary condition can help improving the chi-square over time or not? I mean, do you think you can really track the compliance of this dynamo compared to the Earth? Let me rephrase it, sorry. Do you think that imposing another boundary condition, you will get more often a good chi-square, a chi-square which is more in agreement with the Earth?
Well, based on the amount of work that's been produced in the field with either imposed temperature or imposed fluxes, I would say that each of them can lead to a significant chi-square, provided you get the usual ratio of timescales wrong in the right proportions.
Well, basically, if you say that you get poor compliance mainly due to too large dipole component, I mean, the remedy would to drive a little bit harder, crank up the ready number a little bit. That typically will do the job. Reduce the relative dipole.
And also Kathy told us on Wednesday afternoon that maybe the most recent field, say, in the last million years or was not very typical. Kathy, maybe the chi-squared is not, well, maybe it should change over time, I don't know.
I think it's an open question whether the last few hundred years is entirely representative. We know it's not. Because
yeah, okay. But it remains that this is what we know best.
Absolutely.
Yes.
Mm-hmm. This would make things even worse because you say
yeah, it's too. Yes. So crank up the ready number, Alex, in your simulation. Yes. Yes.
Well, most of the well.
So you wouldn't get a reversal in this case. Or you have to wait a long time.
No.
Concerning the South Atlantic anomaly that Chris was asking for, I seem to remember that there is a region of flux emergence or radial flow, which is 180 degrees away towards the east. So I think that will be where you would think the gyre comes closer to the surface. So there is at least no direct connection. I think people like Haggai looked into this more in detail. Okay, there was a question here. If you can parse the mic.
Thanks for a good talk. I was just wondering, you had that plot of how flow changes in the northern hemisphere from observation, and then around the 80s, there was, or was it the 70s, there's like a really big increase in two of your virtual flow observatories.
Sorry,
yeah, that's a while back.
This one?
That one, yeah. Around the 60s, you have the red and the blue line really dipping in either. Yeah, they are.
You mean like
yeah. And then you have
synchronously?
The other one doing the opposite. Has anyone looked into that? Either Alex or anyone else in the room?
No, I didn't notice that when I made this plot. So I looked into it. Yeah, I'm sorry. I couldn't. Okay.
If anyone has a spare hour, then.
Okay, with that, let's thank Alex again. It's time for tea and coffee, and we reconvene at 11:15.